This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. And on today's lecture, we are going to continue talking about clustering and unsupervised learning. But before we start with new clustering algorithm, just to have a brief recap. Just going to reduce the volume here. Okay. Maybe if I stand still. This is way too frequent. Okay. Okay, I'm just going to stand here for 50 minutes straight. That's fine. Sorry about this yet again. I'm not lucky with microphones, really. I hate them. Anyway, just before we continue with the new clustering algorithm approach, we just have a quick recap of what we started talking about on last lecture. So we talked about the main ingredients in general for clustering, and they are, what are the main ingredients for doing clustering? Can anyone tell me? Distance metric, yeah? Can you say that in order? Let's see if you have a good memory. What's the next one? Yes, you need to be able to evaluate how good a cluster is or how... You definitely need an algorithm as well to generate your clusters. And our definition of cluster is basically a region that are very cohesive. So we'll be looking for intra-cluster cohesion and optimizing that, and also optimizing inter-cluster separation. So points that are close to each other and separated for the rest. And that's our definition of clustering. And one point that we tried to make clear previously also is that clustering is quite subjective to an expert. And of course, we need a clustering algorithm. And the clustering algorithm will basically optimize a function that could be either optimizing inter or inter-cluster separation. And we discussed different ways to cluster algorithms. No pun intended, but we can basically group them in 4 classes if you look like this. For instance, we have clustering approaches that are exclusive. Exclusive clustering will mean each data point you have will be assigned to one and only one cluster, while overlapping clustering would allow a probabilistic view of the clustering. So they could be assigned to multiple ones. And also, broadly speaking, we'll have clusters that are hierarchical or partitional. Okay? And we can also define clustering approaches based on their cluster definition. So a different way to see these 4 classes would be something like this. For instance, let's consider k-means and k-medoids that we discussed on Wednesday. They could be seen as centroid-based because their notion of cluster is based on a centroid, which defines something called a Voronoi tessellation. Does anyone know what a Voronoi tessellation is? Okay, so basically, what this means is this will define an area or a cell in space, and its basic definition is every single point inside the cell is closer to the centroid than to any other centroid. Okay? So basically, we're drawing lines that are equidistant between two centroids. So everything that inside this area is closer to this centroid. And that's basically what k-means does, right? So based on a given set of centroids, we are going to assign for each point what's the closest centroid I have, okay? And that's one way to view k-means, which is a partitional algorithm, exclusive algorithm that requires as an input a number of clusters you like. And we can have also connectivity-based approaches, for instance, hierarchical. And their notion of clusters will be a cutoff for a given dendrogram. Okay? So when you do hierarchical clusters, we will end up with a hierarchical scheme for each of the data points. And where we use that a lot for phylogenetic tree reconstruction. In phylogenetic tree reconstruction, we are interested in how things are connected, not necessarily on a cutoff. But from a dendrogram, we can generate a given number of clusters, basically selecting a similarity threshold. For instance, if we select this similarity thresholds, we'd end up with 3 clusters. If we move one step above, we will have 2. If one step below, we'll have 5. Okay? This is a different way to see clustering approaches. And we'll have a third way, which is density-based. So in this case, the notion of clusters is a connected region of high density. Okay? And today we're going to focus on a very special and very important algorithm, density-based algorithm, which is dB-scan. Okay? And we also have distribution-based approaches, which instead of calculating distances, distribution of features will be used to describe the clusters. For instance, each cluster could be described as a Gaussian. And then we can have a generative model. One of the examples of these methods are mixture models. And then we have basically a function that would describe the cluster, and then we assign points that fit that function. And on the previous lecture, we talked about k-means. And even though it's probably the most widely used method, it's a very simple method. It's a scalable method. What's the time complexity for k-means? Can anyone tell me?
It's very sensitive to fault line.
Could you tell again? Sorry. I'll stay here. Yeah.
It's very sensitive to the outline.
Yes, it is. But what's the time complexity? How does the running time is affected by the size of the input in k-means? It's pretty much linear. So it's affected by the number of points, by the number of iterations you require, and by the number of clusters. So T, K, N. Iterations, clusters, and the number of data points. And we always consider that it's fair enough to consider that the number of iterations is small. K-means converge really quickly, and the number of clusters usually is considerably smaller than the size of your data sets. Then you can consider it linear, but it does have limitations. And as he mentioned, it's fairly sensitive to outliers, but also k-means is fairly sensitive to different cluster sizes. In this case, for instance, you won't manage to pick up the different sizes of the clusters, but also different densities. So if you have 3 clusters, and we clearly can see 3 clusters from here, given that k-means is using the mean for that tessellation cell, it will struggle to separate these two because they have different densities. Okay? It will try to divide the space fairly, which is not always the case. And also k-means it struggles with non-convex clusters. Okay? Something like this. And as mentioned, k-means is quite sensitive because it uses a mean to describe the centroid. So if you have an outlier, that's going to affect quite a lot the mean. What can we do to solve this outlier issue? That's what k-medots does. Instead of the mean, we can consider, for instance, a median, which is a metric that is less sensitive to outliers. But still, you struggle with different sizes, different densities, and non-convex clusters. And so what can we do to actually cluster properly when you have these kind of problems? And one of the approaches we can use is density-based clustering. So the basic concept behind density-based clustering is clusters are dense regions in data space separated by lower object density. So for instance, in this example, we'll be looking for regions that are dense, and they are separated by regions that have lower density. And basically, for any point in a cluster, we will need that the local point density around the point has to exceed some threshold. And we'll call this threshold epsilon. So to call a region dense, I need to have at least a given number of points. Okay? So that's one of the usual input parameters for distance-based clustering. And we will also require that the regions of density are connected. So the set of points from one cluster is spatially connected. Okay? So the main features for density-based clustering is it's capable of discovering clusters of arbitrary shape, so it doesn't assume a given shape, or for instance, like k-means will try to divide the space in hyperspheres, so it can discover clusters of arbitrary shape. It better handles noise and outliers. And for instance, while k-means will fail in examples like this, density-based approaches are more effective. For instance, in this case, we do have 4 clusters here. If you use k-means with the k equals 4, it's going to fail, because it will fail to identify this non-convex curve here, and this one here, this one here, and this one here. If you have clusters of different sizes as well as regions of different density. So what we do, we try to use a density-based clustering algorithm, and one of the most famous ones is dbScan, is the one that we're going to focus on today. dbScan. So dbScan is the first density-based algorithm ever proposed. It was proposed by Martin Nestor in a conference in '96, the Knowledge Discovery and Data Mining Conference, a very important conference. It's one of the top cited clustering algorithms, and it's widely used because it's still quite efficient for small data sets, and it doesn't have so many drawbacks as k-means. And the intuition behind dbScan is, once again, this is general for density-based clusters. In general, a cluster is a region of high density, okay? And it will also consider the notion of noise or outlier points that will lie in low-density regions. And the thing with dbScan is it will ignore these points. This won't be part of the final clustering. So in a way, you can use it even to detect outliers and detect noise from the data and remove it. So what we need to do for dbScan to work is first define a neighborhood of our data points, and I'll get to that in a sec, and define what high density is. So for dbScan, we're looking for high density regions that are connected. For that, we need to define what a neighborhood means and what high and low density means. So for dbScan, the neighborhood, so we're going to call epsilon neighborhoods all objects within a radius of epsilon from an object. So neighborhood epsilon of a given point P would be every point Q, given that the distance between them is lower than epsilon. So everything that is within, let's say, a radius. And that's one of the input parameters of dbScan. And the second one would be defining what high density means. And high density will be defined as the following. So a given epsilon neighborhood of an object contain at least a minimum number of points or objects. And these two together will define what is density for us. Okay. So I'm going to stay really still. I'm still. I'll hold my breath if necessary. That's good. I'm advanced scuba diver, that's fine. So we have basically 2 input parameters for dbScan, an epsilon and a high density, the minimum number of points given that radius. That will give us the density. Well, as you can see, it's quite different for k-means. I don't need to say I want 5 clusters, 10 clusters. Instead, I just define how dense I want my clusters to be. Okay? It's very similar, very different in that way. And so we consider 2 points, P and Q, for a given epsilon neighborhood, we're going to say that the density of P is high if we consider the minimum number of points as 4, because we have the point P plus 3. So we have 4 items in its neighborhood. So P is highly, in a region that is highly connected. And Q will be low because it only has 3. Okay, it's a very simple definition. And given an epsilon and a minimum number of points, we can categorize our data points into 3 groups. We will have a core point, and core points will have at least a minimum number of points within a radius epsilon. And these points, we will allocate them on the same cluster. For instance, if we consider the minimum number of points in this example as 5, this will be a core point. It has 6 elements in its neighborhood. This will be a core point as well, but these won't be. For those points that are connected, are in the vicinity of a core point, but they don't reach the minimum number of points, we call them border points. Okay? So we have a few points, then the minimum value within its neighborhood, but it's connected. So it's in a neighborhood of a core point. For instance, this one. And most likely this one as well, if we consider the minimum points of 5. And we have the third category, which would be an outlier or a noise point, which is any point that is not either a core or a border. So it's completely disconnected. Okay? And these won't be included in the final clustering assignments. So DB-scan will have basically 3 important concepts to discuss. One is density reachability. So direct density reachability will be the following. So an object P is directly density reachable from an object Q, so from Q, if Q is a core object and P it is in its epsilon neighborhood. So basically, if all the objects that are within its neighborhood will be directly density reachable. Okay? And so P is directly density reachable from Q, but not always the opposite. Okay? So Q might not even be, one of them might not be a core element, for instance. And so therefore density reachability is a asymmetric relationship. And the other concept is just density reachable. So we have direct density reachable, and we have density reachable, which is basically a point is P is density reachable from a point Q if there is a chain of points, P1, P2, until Pk, with P1 being Q, Pk being P, so the first one and the last ones are our points of interest, such that every point in between are directly density reachable. In that way, there is a chain linking one point to the other in a connected dense region, which is also an asymmetric relation. And we have a third one, which is density connected. So we say a point is density connected to another if there is an intermediate point V such that they are directly density connected. So we say Pu is density connected to Q if we have an intermediary point that it's connected to P and to Q. Okay? And in this case, it's a symmetric relationship. And basically, the cluster definition for DB will be the following. So given a data set of D points, so it's our input data. And we also have 2 main parameters that will affect how clusters will be found. Epsilon and the minimum number of points, which will define our density. So a cluster C will be a subset of D, satisfying mainly 2 criteria. The first one is maximality. So maximality will say basically that for all P and Q, 2 data points, if P belongs to a cluster C, let's consider that. So P was assigned to a given cluster. If Q is density reachable from P, then Q also belongs to C. This is to say we are connecting every neighborhood that is reachable. Okay? And that's how we expand from a given point to the others to expand the clusters. and connectivity. For all P and Q belonging to a cluster, they are both densely connected. So this will say how do we expand them, and this will guarantee everything is connected. And the ending cluster will contain both core and border points. And the noise and outlier points, they will not belong to any cluster. That's one difference from dbScan from other hierarchical and partitioning algorithms. So basically, dbScan algorithm will follow like this. So we have 3 input parameters, our data points, representing from a given set of features in a given n-dimensional space. We have our neighborhood, so the radius for our neighborhood, the minimum distance, and the minimum number of points to say a region is densely connected. So what dbScan will do is we'll proceed arbitrarily picking or scanning point by point until all points have been visited. And so basically, if a given point that is starting to scan is a core point, meaning it has at least a minimum point within its epsilon neighborhood, we're going to collect all density reachable points from P and assign it to a new cluster. Okay? And we assign P to noise otherwise. But we won't ever reassign labels. Okay? Once a point is assigned, it doesn't get assigned again. Okay? So basically, the procedure then will receive our data sets, our epsilon, and a minimum number of points. And we're going to iterate. And this doesn't need to be in a specific order. It could be arbitrary. So for each unvisited point belonging to that initial set, we'll mark it as visited. We'll get its neighborhood based on a epsilon. And we'll define then if it's a core point or not. So if the number of the neighborhood is smaller than the minimum number of points, we mark it as noise. Otherwise, we'll set it to a cluster. And for all points in its neighborhood, we'll consider recursively finding everything that is density reachable, basically getting the neighbors of its neighbors and expanding this region of connected density, per se. Time complexity and space complexity of dbScan. So what will be the time complexity of dbScan in your opinion? So we need to iterate through all points, right? So let's say we have a data point size of n. And for each of them, in each step, we need to find our neighborhood, which is potentially will vary across all points again. So we have basically a quadratic time complexity, okay? Because to identify the neighborhood, we need potentially to vary and iterate through all points again. So n times n, so we have a n squared there. However, this is a very naive way to implement. So if we implement dbScan a bit more wisely, for instance, using a spatial matrix index, let's say a given point can efficiently find its neighbors, we can drop down the complexity to n log n. Okay, for instance, using KD3 or something like that, we can basically, on low dimensions, if we don't have too many features representing each data point, instead of running through every single point to find the neighbors, we can find it in a tree, which is basically, the cost for that is the height of the tree, which is log n. So n times varying through all points times log n to find each neighbor. And in terms of space complexity is linear. And an interesting thing then about dbScan, it can handle, as mentioned, arbitrary shapes. So if you have an inputs data set which looks like this, dbScan will be able to correctly assign dense regions. If that's the correct answer for you or not, that depends on your expert evaluation of whether these make sense or not. And as you can see, a lot of the data points are left out from the cluster. So it's not valid for every application, but it might be interesting as simply a way to identify outliers on your data. And as you can see here, you have a great variability in terms of cluster sizes as well, which dbScan can handle. So there's no assumption in terms of cluster size, and it's quite resistant to noise. as well. Sure.
Can you just play with the spatial indexes again?
Imagine the following. Each data point, let me just go back to see if I have an example. Yeah, imagine each data point is represented by just 2 features, just to be simple. Okay? 2 features. So you have n data points and you have 2 features per data point, right? You can put your 2 features in a list. And for a given point, you can ask the question, what's the closest one? Or what are all the points within a given threshold, which is epsilon? To do that, you need to you need to iterate through the whole list, right? Which is O of n, linear. You can do that quickly if you have a spatial representation of your features. So if you represent your feature as a tree, your feature space as a tree, you can do binary search to find your neighbors. So it's just a more efficient way to find your neighbors. And there are quite a few ways to do that. So for spatial index, you have KD trees, you have R trees, but they're basically on, I'm going to divide the search space. And let's say we divide the search space in 2, and then we keep dividing it in smaller bits. And in each iteration, I choose which side it is. Imagine you divide it in quadrants, right? So you divide it in 2 first, then in 2 again. So in 2 iterations, you divide it in 4. In 3 iterations, divide it 8, then 16, then 32. And then the number of steps you need to cover everything will be log n, because you basically have a binary tree. So it's just a neat way to do spatial representation. That's good when you need to find neighbors. Not only for this case. If you need a quick way to identify neighbors for a given set of points, you can do spatial indexing. And that's a huge difference. So you go from something that is quadratic, that grows fairly quickly, to something that is more scalable. For large data sets, it makes a huge difference. And DBScan is quite efficient in terms of space complexity as well. So you can find then arbitrary shapes. It can handle clusters of different sizes. It handles noise really well as well. And if you compare DBScan versus k-means, of course you have a few instances that k-means will be more interesting than DBScan. Remembering k-means is still linear, still more efficient. And sometimes you do know how many clusters you're looking for, right? So k-means might be appropriate. When you don't, DBScan might be a good idea. Okay? So if you look at these 3 examples, if you have no clue how many clusters you have, and you tell k-means we need 2 here, it's going to group these here. While DBScan, by just defining what density is, will be able to pick up how many true clusters you have. Okay? And of course, this is pretty obvious because we're only considering 2 dimensions. This is not so obvious you consider 100, 1,000. Okay? But it does mean that if you don't have a clue about the number of clusters you're looking for, DBScan is a good alternative. You still need to fit the other parameters, which is density and the minimum number of clusters, and you need to optimize it for your problem as well. But you don't have to give the number of clusters. And for non-convex forms like these 2, again, k-means will struggle, basically trying to divide the space into and defining the Voronoi tessellations. And since DBScan doesn't consider any specific shape, we'll just consider things that are dense and connected. We'll be able to find non-convex clusters as well. However, DBScan still have weaknesses. And for instance, if you have a goal like this, so you have 6 clusters. Some of them are overlapping with others. Some of them have large diversity in terms of density. So this could render completely different clusterings if you change, for instance, your epsilon configuration. So DBScan struggles a lot with overlapping clusters if you have something like this. So if you use a given epsilon here, you can find, for instance, 3 clusters. But you won't be able to differentiate between these because these regions are basically connected. So you don't expect to be able to put them apart because they are connected for that given epsilon. So if you want, let's say, to separate them, you need to be more strict in terms of density. So I want a higher density. But if you do that, well, you can have the 3 clusters apart, where everything else is on a different cluster. So it's a compromise of what you do. And DBs can still have a couple weaknesses, even though it's more reliable than k-means. And of course, you don't need to say how many clusters you want, but defining the epsilon and the minimum number of points can be tricky, as it is tricky sometimes to define the number of clusters you need for k-means. But there are a few ways to do that. And DBscan, you can determine the parameters basically doing this. So you can calculate the kth nearest neighbors. Let's say you're using a given number of points, and I'm going to calculate basically calculate all your neighbors. What's the kth nearest one for each of the data points? Let's say we plot each of our data points on X, and here we have our k distance, and we sort it. Either ascending or descending, it doesn't matter. And we can set epsilon to the maximum before we see a jump. And the rationale here is basically that, by definition, we expect the noise points will have the kth nearest neighbor at farther distance when comparing with points that are in clusters. So you'll see something like this. So 8 given clusters and more or less a similar kth distance between them. Same thing for another cluster, and suddenly we'll see that all noise points will have larger distance, increasing larger distance. So a good estimate for epsilon will be this threshold point here. So the maximum before everything starts growing quite quickly. And that's basically density-based clustering. And previously, we already talked about hierarchical clustering. So this is basically a recap, because previously for phylogenetic tree reconstruction, we focus on the bottom-up approach of hierarchical clustering, which is agglomerative clustering. Again. And basically, agglomerative clustering means that each data point starts on a single cluster. I'm just going to lie down and stay here. On a single cluster, I'm sad now, on a single cluster, and what you're going to do at each step, you join them together until you have one big point. I'm going to lie down and cry, because that was quite upsetting. Oh, yes, why not? It's Friday. Yeah, so basically, you can't see me, but you can hear me. Each data point will start in a single cluster. That's why it's bottom up. And we'll keep iterating. You can't see this. Yeah, joining cluster into big cluster until we reach one single big cluster. And we have different ways to do agglomerative clustering, right? What's the difference between them? The difference is, and we talked about this already, which are the next cluster to merge. And basically, we have, with our laws of generality, 3 options. We can say we're going to merge the closest ones. That's called single linkage. We can get the average, which is average linkage, or the furthest one, which is complete linkage. Okay? UPGMA, which is a agglomerative clustering algorithm for phylogenetic trees. Which category is UPGMA? Which one? Average linkage. Yep. And that's basically the bottom up. Okay? And you're all saturated to hear about it. But you can also do the opposite. You can have a divisive hierarchical clustering, starting from top down. Instead of starting, each point is a single cluster. Nope. Everybody's on the same cluster, and at each step we split them into smaller clusters. So we can stop when we reach a desired number of clusters, or we can do the full dendrogram again, and until each point is in a singleton. And visually it will be based like this. So you still need a distance matrix, which we are all familiar. And with agglomerative, we start with step 0 with everybody in a single one, and we keep putting them together. Divisive, step 1 will be this one, and we keep dividing them. And interesting thing about hierarchical clustering is it gives us dendrograms, and dendrograms are quite powerful visualization tools. And they can tell us a lot about outliers as well. Not only DBs can, but you can try to identify outliers with hierarchical clustering as following. Isolated branches would mean that that point is quite different from everything else. So basically, a point like this on a dendrogram will be an isolated branch. And you can then identify this doesn't belong here, perhaps. I need to take a closer look at that. And that's quite interesting to detect outliers. And also to visualize patterns in your data. For instance, if you do a dendrogram on the columns and lines of a given matrix you have, for instance, a heat map matrix, and you sort them, the columns and lines, based on the cluster IDs, basically putting clusters together, you start to identify patterns that are common to a subset of those items, okay? So that's quite interesting to understanding your data. And something very interesting about divisive hierarchical clustering is usually more computationally expensive than bottom-up. And actually, you can implement the divisive hierarchical clustering basically with any partitional algorithm as long as it generates a fixed number of clusters. How? Good exam question. So I'm not going to give the answer. So how would you do that? Let's say get k-means. How would you create a top-down hierarchical clustering using k-means? No cheating. Don't look at the slides. You already have access to it. Think about it a little bit. This could be actually, this is the kind of question that you go from the concept to something that is applicable. How you generate a hierarchy of clusters top-down using a partitional algorithm. Which k-values, for instance? 1 to 10, okay. Go through your algorithm then. First thing, you have 10 items in a single cluster. What do you do? No. Let's say you have 10 data points. And your first step is well, that's your initial step, yeah. So everything's in one cluster. Two, yeah? Keep going. Yep, so set the number to 2, for instance, to 3, it doesn't matter. But you can keep, if you want a binary tree, yeah, definitely k equals 2. And you keep partitioning them iteratively. That's exactly it, okay? So you start with everybody in a single one. Let's say k-means equals 2. You end up with these 2 clusters, and then you keep repeating it. So apply k-means equals 2 to this one, and you stop when every single point is in a singleton, in a single clustering. So this is an easy way to do divisive clustering, hierarchical clustering with a partitional algorithm. What's the problem with that in terms of efficiency? That it's considerably less efficient than bottom-up, right? And that's it for today. Just a quick announcement. It's assignment time. So assignment 1 is ready. It will be released in an hour or 2. It will cover everything we've seen until today. And the thing is, it will be released as a Jupyter notebook. It will be available on LMS. It will be available on our server. It will be available on the GitHub repository for this subject. So everything you need to do is fill it up with code and answers for the questions and submit it again on LMS via Turnitin. So we only accept Jupyter notebook files. You don't need to send anything else. Make sure you don't zip it or anything. Just submit it filled up. Okay? Thank you very much and enjoy your weekend. Hi. Sure. Yep.
This cluster rate. So when after maybe this step we set the cluster k equals 2, the next step, how do we increase the k?
You don't increase, you just keep it 2.
Just give it 2 and
Yeah. So this
apply
way,
on the left branch and the right branch. Like
yes,
this.
until you get a single point in a single cluster. So the thing is, if you get k equals 2, you end up with a binary tree. That's the thing, right? So you have your tree, right? So let's say the circles are nodes, right? And each parent will always have a son and a daughter, for instance. That's why equals 2. You could do equals 3, and then you have 3. Okay? But considering in most cases we'll be looking at binary trees, k equals 2 means we're always dividing. Yeah, sounds good. Not a problem.
I have a question about the algorithm. So this is an example, and then I understand, for example, like a star from A.
Is this from Hannah or something?
Yeah. She wrote that.
Okay.
I understood it in the morning, but in the afternoon when I take it down and then the list down, okay, I forgot. Then how could get like it's 2 plus?
Can I just put it here?
Yeah.
Just so make sure. Okay, my flasher has battery.
Yeah.
So, okay.
So example is GT and G, and then for example like A and B one is one, so it's GT and it's A and G.
Can I explain with my example?
Yeah,
Maybe it's
that's
easier.
good.
Because
Yeah.
that one I understand.
Yeah.
And it's not someone's handwriting, which is good.
Yeah.
Sorry, just a second. So, which week is that? So it's week 2, isn't it? Is it week 2 or 3? 3? Let's try 3A. Nope. It's not 3. It's probably 2. Let's go to A. If not, to B. Because the problem is Lieberstein, the definition of Lieberstein is recursive.
Yeah.
I don't recommend anyone to try to explain the recursive algorithm by actually following it up. Because you need to think about the recursion heap as well. What's your background, if I may ask?
Bioinformatics.
Bioinformatics, yeah. So, yeah, Lieberstein. And this is the Lieberstein, right?
Yeah.
So, I don't have pen, I should, okay. So, what would you like? Lieberstein of A, B, what was the example? I don't remember.
A, B, and
Let's say
and
A,
G.
C, B, or something like that.
Yeah.
What's going to happen, don't try to actually follow the algorithm because it's recursive. It's quite difficult for us if you have too many recursive. It grows as a tree, and then it goes back. So basically what you need to do about Lieberstein, you have A and B, right? And these are the conditions to return.
Yeah.
And when you return, you assemble your score. So what's the Lieberstein distance between these two? So Lieberstein will accept indels and substitutions. And we can easily know that this is just an indel.
Yeah.
So what we're going to do is, so Lieberstein, the options we have are, we have a indel from A, and I'm basically saying, well, I have an insertion in A, if A is larger than B, for instance, or I have an insertion in B, if B is larger than A. So this is a indel cost, 1 and 1. Or I can have, I move on both of them. So basically, A, C, C, D. So let's say for this one, what's going to happen is we're going to have, first of all, a match. When you have a match or a mismatch,
Sorry, for the one is from this one, or like the one is.
it's always going to start this way
Okay.
because of this. So
Because
this
of
is
the
the
different
representation
things.
is I remove the first one, I continue with the rest. So A1, this is, I have a string strip the first character,
Yeah.
submit the rest.
Okay.
So we go from left to right.
Yeah.
Because of this is Python, that's how Python does. It
Yeah.
doesn't matter, you could implement it the other way.
Okay.
So we'll have first a match, or a mismatch score, and then this will be, for instance, 0 if they're the same, and 1 if they're different. Okay? So what Levenstein will do is recursively partition this in all possibilities. So it's going to test everything. So you're going to have permutations and combinations of all of them, and will basically return to you the minimum.
Yeah.
So first off, AB, ACB, and we were going to try the minimum of having a indel in one side, an indel on the other side, and a mismatch. And when we go again, okay, so this will call Levenstein again, this will call Levenstein again, and again. So it will be like this. I have a first call here, and I have 3 calls. Always a tree with 3. And this is indel in A, let's say it's AB, right? Indel in B, and a mismatch or a match, right? So this again, so when you say it's an indel in B, in A, you're basically removing 1. And this will make another call, which is indel in 1, indel in the other one, a mismatch. And then again. And then again. So this is going to create the tree, right? And when we do the backtracking, which is the return statement, would be if we have length of A equals 0, what does that mean? I have removed enough items from A, right? So meaning, for instance, that I have an end gap, I have an end region of insertions or deletions in B. So I basically return what's left. So if you read something like this, so A, B, C, D, A, B, C, D, E, F, this would be insertion. So we finish A, we need to return the number of penalties we'll have for indels in B. Same for A. Or we return a mismatch score. So this is going to calculate all the possibilities. And they're going to be summed up. And we're going to get the minimum value of all these trace bags here. For instance, let's say it's this one. That's how you understand recursion instead of actually trying to first round, second round, third round. You need to understand what's going on here. And how I trace back. The most important thing is once I reach a return point, how this is going to compute my final answer. For instance, are you familiar with Fibonacci points? Fibonacci numbers? So Fibonacci is a function. The Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. So fib of 1 is 1. Let's say fib of 0 is 1. And this is my fib a or n, fib n, and that's basically my function. You don't need to go one by one. You just need to understand that recursively, that's what I need. I don't need to know what's the actual instance here. I just basically need to know that this is going to create a binary tree until I reach a value 1 here. Whoopsie. Or a value 0 here, or a value 0 here. And this will get summed up on their return function until I have my answer.
Okay.
That's the best way to understand recursion.
Yeah.
Yeah?
Yeah.
Not sure if that helps to understand how Levenstein works, but
Yeah.
that's how you program recursively. You never try to trace things back. It works for 2 or 3 letters. It's not helpful. You're not going to work with 2 or 3 letters. Proteins have hundreds and hundreds of positives, so yeah. As long as you understand, I can have these 3 possibilities, and I want the minimum between them. So
Okay.
you can do this iteratively as well. If you don't want recursion, you can use for loops, while loops. You can calculate Fibonacci iteratively. It doesn't need to be recursive.
Okay.
That's a good exercise to do.
Sure.
Get the same. Try to do Levenstein iteratively.
Okay.
It's not easy, but yes, that's why recursion is so powerful. But it's understanding how it works rather than trying to follow up the examples. Does that make sense to you?
Yeah. Thank you very much.
Not a problem.
This progress means just put string static here and move another string from right to right and do the match.
Can you say that again? I think that's correct, but can you say it again?
Like this.
What Levenstein will mean, or which one you're talking about?
This.
Yeah.
That means move another string from left to right and do the match.
No, not really, no. Do you understand why the complexity is 3 to the end? Why it's a 3?
Why 3? Because there's 3
Options there.
yeah.
Every time you have 3 options. So each iteration will cover 1 character. N is the size of the largest sequence. So in a worst case scenario, you need 3 times 3 times 3 times 3 in each level of your tree. So in each level of your 3, you're testing the 3 options. You're testing every single one of them. It's not just screening back and forth. No, I'm testing every single possibility. Left and forth, indels, everything at once. So this is a very powerful way to describe it because it's so concisive. This is doing insertions, deletions, and mismatches. So this is a way to represent all the vast complexity of this. And it's 3 to the end because, let's say, our sequence has 100 characters. Right?
Yeah.
The first one, this is 1 character. Let's say it's the first one. So the first one could be an insertion, deletion, or substitution. Then I go to the next one. Then I go to the next one. So 3 times 3 times 3. So 3 times 3 times 3. How many characters I have? 100. So this is n. 3 to the n. But it's recursion. So it's the way to see it is as a 3 where each node has 3 children. Okay? And that means I'm testing every single possible combination of insertions, deletions, and substitutions, matches, mismatches. That's what this is doing.
So this is
The better way to visualize is in this tree. And when it reaches the bottom, it's going to return, right? And these are the return values you're going to give it. And basically, this minimum will say is, I want the minimum value for one of the paths from root to leaf, one of them, out of 3 to the end. Okay? Don't try to visualize it as, oh, you're doing this and that, because this is basically a tree that will explain your whole search space. This is extremely slow. Okay? It's just an example. Okay? Is that clear? Yeah? No problem.
about the spatial indexing.
Sure.
Yeah, so
We're not going to cover that on assignments or exams, so it's just out of curiosity. But yeah,
it's
sure.
out of curiosity.
Don't worry too much about it. Yeah.
Like, what's the general idea?
General idea is, okay, I need more paper. I don't know who this is, but it shouldn't be here. So let's use it. Let's consider two-dimensional grids, because it's easy. If you have k points on a vector, 2D, so x and y, right? X and y for each of them. And they are here. I want the minimum value in k what do I need to do? Search them. O of n. If this is represented in a spatial, what's the name? Spatial index. I could try to represent my space, 2D space, as a tree. And I do binary search.